Hello. In this video, we are going to discuss the relation of current with the drift speed, the expression for drift speed that we had obtained previously, that is Vd is equal to EV divided by m into L times of tau, where the symbols uh, were having their own meaning. That is, E stands for the charge of the electron. Now this is in magnitude form because we know that the electrons drift in the direction opposite to that of the uh, field. So here we are considering or concerned with the magnitude only, where E is the charge of the electron, V is the potential difference across the conducting wire, that is of length L, that is in the denominator. Me gives or is the mass of the electron, and tau here is the relaxation time. And as we know, the relaxation time is the average of all the individual time taken by each electron considered between two successive collision, which was explained in the previous video in this current electricity series. Now we are to obtain, obviously because the electrons are flowing, because we will be definitely having a current that can be calculated. And so now we are uh, concerned about the relation between the current and the drift speed that we have over here. Now if I consider a conductor, again I'm considering a segment of the entire conducting wire, and this is a highly magnified view of it. So this is the segment of a wire conducting the current, and in that we have the area of cross section is A. One of the electrons travels from one end of the conductor to the other. Of course, there are plenty of electrons, but as of now, I'm considering just one electron. Now, this electron, obviously, this is the positive end of the conductor, while this end is negative. Now, as the electron travels from one end to the other, it travels with a speed which is equal to the drift speed. And obviously because there are plenty of electrons, so that is why we have the drifting case over here rather than just shooting of the electron from one end to the other end at a faster rate. So as we have the drift speed is equal to the length of the conductor. We can say that it is equal to the length of the conductor divided by the time taken. But if we have the length to be equal to the drift speed, then the time must be equal to 1 second. It's quite obvious because on the left hand side you have Vd. Okay, so for this is for L equal to Vd, we have the time taken for the electron to move across this length of Vd that we are considering. The time taken will obviously be 1 second, isn't it? So with this idea in our mind, we proceed as follows. See, if we are considering n as the number of electrons that are present per unit volume of the given conductor. So the total number of electrons that are present in this, the total number of electrons that can possibly be present in this arrangement that we are seeing over there, in this arrangement. So the total number of electrons that are present, let us say, that is equal to capital N, and that must be equal to the number of electrons present per unit volume, that is N, that we have taken over there, multiplied with the volume of the segment that we have considered. Now the volume of the segment in this case is equal to the area multiplied with the length. So n gets multiplied with the volume. Volume is equal to the area of cross section that we have taken as A, and the length in this case is equal to or is having an equal magnitude to that of the drift speed of an electron. So this being the volume, now we have the total number of electrons that are present. So what is the total amount of charge that is present? As far as charge quantization is concerned, we have the total charge within that volume to be equal to Q, and that must be equal to, as far as charge quantization is concerned, we have total number of electrons, that is capital N, multiplied with the charge of each electron, that is E. So we have this value to be equal to we put the value of N over there. So N is simply Na times of Vd multiplied with E. So we have the total charge to be equal to Q, which is equal to N. Rearranging it, we have NEA times of Vd. Now this is the charge flowing obviously in what time? The time is 1 second, obviously we have taken over there. So the charge flowing per unit time, charge per 1 second, is nothing but equal to the current. So the current is, in this case, is NEA times of Vd, which gives me the idea that I is proportional to Vd. With this theory in mind, we can say that although the current drift speed is in millimeters per second, but the current is substantial in our household circuit, and that's because of the fact that we have considered N in terms of Avogadro's number, while E is in the charge of the electron is in 10 to the power minus 19, and from that we have the value of I in the order of 10 to the power 1. So with this relation between current and drift velocity with us, we can move further with the relation between current and the potential across the conductor. So as we have I is equal to NEA Vd, and instead of Vd we can use this value that we had just obtained over there right at the top, that is for Vd, and we can just put it over there, EV by ME times of L times of tau, tau being the relaxation time, and that is equal to NE squared into tau. I bring the tau over here on purpose, and divided by ME, and this term can be kept in brackets. I have A outside as well as L. I keep them in another bracket, that is the square bracket over here, and finally I have the V completely outside. V stands for the potential that is applied. So this is some kind of relation over here between current and the potential that has been applied across the given wire or the conducting wire. So what does this relation actually tell us? Now if you observe closely, we have N to be fixed. The number of electrons per unit volume is fixed for a given material of a conductor. Say it's for copper, you have the value of N per unit volume fixed, as well as the charge of the electron E, that always remains fixed. Mass of the electron must remain fixed as well, that does not change. Tau is the relaxation time over, and it's an average value if you remember, and the average value obviously tends to remain constant with no change in temperature or other physical conditions or any kind of pressure on the conductor, the collisions between the average number of collisions between the electrons won't change until unless there is a drastic change in the temperature. So with that remaining, with the number of collisions remaining constant per unit time, we have the relaxation time on an average to be constant over a given period of time. So that is a constant quantity. The area and the length, the physical conditions of the conducting material that has been used, the wire, that remaining constant. We have the entire square bracketed term to be a constant value. So that means I is equal to some constant. Let that constant be some k, and this is a V, that is the potential. Now if we vary the potential across the conducting wire, then obviously that is going to affect the current in a way where we can say that the current is directly proportional to the potential difference applied across the ends of the conductor when the temperature and other physical conditions remain constant, and that is what we know as the Ohm's law. The current depends on the potential difference directly with temperature and other physical conditions remaining constant, and that is the Ohm's law. And this term over here is termed as conductance. Conductance is the property of a conductor which allows the electrons or the current to pass through it or to be conducted through it. Now all those factors that are over there, they contribute to the conductance that is in the brackets, the square brackets that I have placed over there. All those terms contribute to the conductance. Now usually we are concerned about what may restrict or what may oppose the flow of current in a circuit, and that is exactly the opposite of what the conductor allows. So that opposition offered to the flow of current, or that hindrance offered to the flow of current across a circuit, is what we call as resistance. So we have the term resistance to be equal to, is represented by R, and that is equal to the reciprocal of conductance. That means if we consider that bracket over there, we can say that resistance is simply ME divided by NE squared tau L divided by A. Again, I am putting that L by A out of the curved brackets with a purpose, of course. So this is the expression for resistance. Now if I put this thing in the formula between I and V, what do I have? I then is equal to 1 by R times of V. As we know, the constants can be multiplied to any term over there. So we have a V to be equal to the R gets crossed to the other side. So we have V is equal to R times of I, which is popularly the school level explanation of Ohm's law. V is equal to Ri, but the actual definition as far as the physical significance is concerned, we have the Ohm's law as this that I've just marked. That is, Ohm's law states that the current must be directly proportional to the potential difference across the ends of the conductor. With that, we can proceed further with the elements that we find in those square brackets or even the curved brackets, how they affect the resistance or even the conductance. Now before moving over to that, we can consider the units. Now the unit first of all is considered for resistance, and for resistance we have the unit omega, or simply ohm, right? And obviously for conductance we have ohm inverse. For conductance, let me just take it over there. For conductance, we have the unit as ohm inverse, or even it is written as mho, mho, or we can say it's also Siemens. So these are the units of resistance and conductance. Then further uh, looking into the bracketed term over there, we can take it to the next page. Let's first consider the case of resistance. We have resistance to be equal to ME divided by NE squared tau L upon A. Because the resistance is, in case of a conducting wire, now picturize this. You have the electrons. This is the segment of the wire considered. And you have the electrons to be moving within this. If you observe closely that if I increase this area, suppose the wire has now a greater area of cross section, these electrons that were present over there now can move over to this part as well, and the collisions are lessened. The lesser the collision, the greater will be the drift speed, because they won't really hinder each other. The hindrance or the resistance that is provided, or the opposition to the flow that is provided, is obviously because of the packing of the material. Now if I am to increase the area of the segment or the wire that is conducting the current, so as the area of cross section increases, the electrons get a greater area. In that case, considering that, we can say that the resistance will obviously decrease, which is the obvious case because we have R to be related to the area inversely, as you can see in the equation over here. So the R resistance is inversely proportional to the area. Now what about the length? Now if I am to increase the length, let me just take it over that, doesn't really matter. So if I am to increase the length now, what happens is that the electrons will have to move a greater distance to, for a given conduction, they have to move a greater distance. The greater the distance, the greater are the chances of collision between the electrons, because they have to travel a greater distance. They have a greater scope of interacting with one another in the form of collision. So that is why with the increase in length, the resistance, the opposition, uh, as because of the number of collisions, must increase. And that is the reason why resistance, as you can see in the above equation, resistance is directly proportional to the length of the given conducting wire or the conductor. So with these things, the rest of the terms that we see within those curved brackets, the mass of the electron, the charge of the electron, the number of electrons per unit volume, and the relaxation time taken for a constant temperature as well, those terms will remain constant. So what we have over here is that combining these two, what we can say is R is proportional to L divided by A, or we can say that R is equal to some constant, and that constant is taken here as rho into L by A. Now this rho is what we know as the resistivity of the material of the conductor. Resistivity of the material of the conductor. What does that mean? The resistivity is the property which gives resistance to the conductor, because those factors that you see within, and the resistivity does not change. That's the best part of it. The resistivity does not change while the conductor's length or area of cross section may change, affecting the resistance. The resistivity is an intrinsic property of a conductor, of course, for a given temperature, because as the temperature changes, if there is a drastic change in the temperature, the electrons will get excited, and as a result of that, there will be more amount of collision, and as a result of collision, the greater the collision, or the greater the amount, or the rate of collision, I should say, the rate of collision increasing decreases the relaxation time to a greater extent. The average relaxation time that we have obtained over there with the increase in temperature decreases, and as a result of that, with tau remaining in the denominator of this equation that you have over here, as tau remains in the denominator, with that decreasing because of the increase of rate of collisions, the resistance will increase, or even the resistivity of the material will increase. So that is the temperature effect on the resistivity as well as on the resistance, but that is to be dealt later. But as of now, we have the resistivity of the material to be constant for a given temperature, and that resistivity obviously has a unit, and the resistivity there's no need to remember any specific unit, because you can see it over here directly, that R being in ohms, and we have the resistivity, and this length being in meter taken in the MK system, and the area in meter square. One of the lengths can get cancelled and the meter can cross over to the other side, so we have the unit of rho as ohm meter. The unit of rho being equal to ohm meter, you can determine the dimension all by yourself, provided you know the dimension of resistance. Resistance is having the dimension of V by I, that is equal to voltage divided by the current. As you know, the voltage is simply, okay, this is the dimension for resistance in case you have missed it, because I didn't really discuss this one. Dimension of resistance is simply voltage by current. Now what is voltage? Voltage is the work done per unit positive charge. So the work done is ml squared t to the power minus 2. This is pretty easy to remember. You have been doing it right from the time you studied about units and measurements and dimensions. And per unit charge means I have I or A, simply AT, and for current in the denominator, again I have another A. So this is the dimension for resistance, ml squared t to the power minus 3 a to the power minus 2. Now you can use this to find the dimension of conductance as well as the resistivity, which has an extra length in it. That means for ohms, if you have this much, for ohm meter, that is resistivity, you must have m another extra L, that is L cubed t to the power minus 3 a to the power minus 2. That is what we have for resistivity. Now with the resistivity available to us, we can also predict or consider another term, that is in conductance. Obviously, because the reciprocal of conductance is resistance, so the reciprocal of resistivity is conductivity, represented by the symbol sigma. What does this conductivity term mean? The conductivity is simply the reciprocal of resistivity, as the resistivity is the intrinsic property of the material of a conductor, which tells us about how the electrons are obstructed while moving across a given conducting material under the influence of a field. Conductivity obviously tells us that how or what how much is a material capable of conducting any given amount of current across it. And there's a simple definition as far as the terms are concerned, and the unit in this case is obviously the reverse or inverse of it, that is ohm inverse meter inverse, as simple as that. And the dimension obviously will have the negative powers, uh, as in case of resistivity. uh, from resistivity you can use those dimension terms and just multiply the powers by a -1, and that is what we have for conductivity. That is m to the power -1, L to the power -3, T to the power 3, A to the power 2. You can check it for yourself. And with the value of conductivity, or the expression for conductivity, now what is the expression for conductivity in this case? Resistivity has the expression rho equals m e divided by n e squared tau, and conductivity obviously has the relation sigma equals n e square tau divided by me. We'll be using this data, or this expression that is available to us later on while discussing the ionic conductivity, or it's not there in this chapter, of course, as far as the syllabus is concerned. It's later on considered for semiconductors. We'll be using this uh, expression for conductivity, which will help us to get a new expression. That's more or less about the resistivity and conductivity. And as I said, the resistivity is impacted by the change in the temperature the of the conducting material. If there is a drastic change in the temperature, that will result in with the increase in temperature, of course, the resistivity increases, which tells us that resistivity is directly proportional to the change in temperature. Let this change in temperature be represented by delta theta over here, and it is also directly proportional to the initial resistivity. Now, any resistance that we are getting over here, we are getting a final resistance, let that be denoted by rho f. That depends on the initial value of resistance and also the change in temperature. Considering these cases, what we have over here is that the resistivity, or the actually this is the change in resistivity. I must rectify that. Now, the change in resistivity is obviously the difference in the resistance, that is the final resistivity that we are getting with respect to the initial resistivity that we had at an initial temperature. So putting these things together, we can obtain a constant over there, that is del rho, is equal to some constant. The constant here is alpha. Now these two are proportionality symbols, right? Before that I had used, they are not the alpha terms that alpha term that I am writing just now. So this is equal to some constant alpha times of the individual terms that are there, rho I as well as del theta. This alpha is known as the temperature coefficient of resistivity, also the resistance, as you will see later. So this is the temperature coefficient of resistivity, which determines, this is obviously fixed for a material, and it determines how much will the resistivity change for a given change in temperature, given by delta theta. So as I had mentioned over here, del rho being equal to rho final minus rho initial, I can put that over there, rho final minus the rho initial equals alpha times of rho initial times of del theta. So I have rho final to be equal to rho initial goes to the other side, and I have alpha rho initial del theta, and this will obviously be equal to rho I times of 1 plus alpha del theta. This is the expression relating the final resistivity with the initial resistivity of the material for a change in temperature through del theta, where alpha is the temperature coefficient of resistance. As you can see from here, I can just put it over there, that alpha is simply equal to the change in resistivity per unit resistivity per unit degree rise in temperature, per unit degree rise in temperature in terms of Celsius scale or even Kelvin scale. Now obviously, because you know resistivity at the top and resistivity at the bottom, they will just cancel out, so the unit is simply Kelvin inverse or a degree Celsius inverse. And likewise you have the dimension as well to be equal to Kelvin inverse, K inverse. So that is the temperature coefficient of resistivity. Now if I multiply both sides by the length and divide both sides by the area of cross section, then what do I end up with? Consider this last equation that we obtained over here, that whole thing over there. So if I am to multiply, so I rewrite that, rho f equals rho I plus alpha rho I times of del theta, and I multiply both the sides with L by A, the factor L by A. So what do I end up with? Now rho L by A, F is the final resistance of the conductor, and that must be equal to, as L by A gets multiplied with the first term, it is simply Ri. The Ri can be taken common and we have 1 plus alpha del theta as it was previously. So this alpha term that we have over here is also the temperature coefficient of resistance. It's the same thing, and obviously it will have the same units and same dimensions. So as I had mentioned previously, that alpha is the temperature coefficient of resistivity as well as resistance, popularly known as the temperature coefficient of resistance, because we consider the resistance as a whole while calculating the amount of current that is flowing in the circuit, rather than going from the resistivity part of it then to the resistance. Considering the length, area and everything, all the parameters are not considered when we are just concerned about the current flowing in the circuit with respect to the resistance offered by the conductor. So this is what we end up with, the temperature coefficient, and then in the videos, upcoming videos, we'll be discussing about the current density as well as the combination of resistors. Resistors are the wires or the conductors that we are considering. We also have resistors, specific resistors with fixed resistances. We can uh, use those resistances in circuits. So that is for the next video in this series. Till next time, thank you.